In Chapter 6, we learn about how electrons are organized within atoms. However, most atoms don't exist as individual atoms, but rather as atoms bonded in chemical compounds. So in Chapter 7, we're going to talk about chemical bonding and the 3D arrangement of atoms within compounds, or molecular geometry. To begin with, we're going to talk about ionic bonding. In section 7.1, we talk about ionic bonding, which is the type of bonding that exists between cations and anions. If we think about bonding, we recognize that we've divided the elements into two broad categories, metals and nonmetals. This gives rise to three possible types of bonding. Or we can have metals combining with nonmetals, which is what we're talking about in section 7.1. This is referred to as ionic bonding, and it forms as a result of electron transfer from the metal to the nonmetal. The other type of bonding that would be possible is between two nonmetal atoms. This results in what we call covalent bonding, and covalent bonding is a result of the sharing of electrons, which I'm going to indicate as dots here, between two nonmetal atoms. There is a third type of bonding that's possible, which occurs between two metal atoms. This is referred to as metallic bonding, and we see this in crystals of metallic elements, and this is a result of electron pooling. And we're going to be looking at that in Chapter 10. So, why do ionic bonds form? Well, ionic bonds are the result of the attraction between oppositely charged ions, that is, between anions and cations. And the strength of this ionic bond is described by Coulomb's law, and Coulomb's law states that the strength of the attraction increases with the size of charge, and increases as distance between the opposite charges decreases. So in our case, the electrostatic attraction is going to be directly proportional to the product of the cation and anion charges, and inversely proportional to the sum of the cation and anion radii. That is, big charges give strong bonds, and small radii, little ions, also give strong bonds. If we just look at a pair of one cation and one anion, like we see in sodium chloride, what Coulomb's law is telling us is that as the ions come closer together, these opposite charges are going to interact more strongly. But what we should be aware of is if they get too close together, the positive nuclei of each of these ions begins to repel and the bond weakens. So for every ionic bond, there will be an optimum distance for those ions to be apart, which we call the bond length. So here's an example problem from the OpenStax book. It says, for which of the following substances is the least energy required to convert 1 mole of the solid into separate ions? So we're looking for the weakest bond. And there are some things that we want to remember. We want small charges, and we want big ionic radii. So let's think about the charges. We're going to have +1, +2, +3 for groups 1a through 3a, and then we're going to have -7, -1, -2, and -3 for groups 7a through 5a. So magnesium oxide, magnesium's in group 2A, so it's going to be a +2. Oxygen's in 6A, so it's going to be a -2. Strontium is also in 2A, and oxygen is still in 6A. So we have to think about where magnesium is and where strontium is, and we can see that magnesium is smaller than strontium, so therefore that's going to form the stronger bond. So the stronger bond out of those two is going to be between magnesium and oxygen, so we'll get rid of that one. Now, when it comes to the last three here, we can see that they all have the anion, fluorine, which is over in group 7A, and then we have potassium, which is over in group 1A, cesium, which is right at the bottom of 1A. So cesium is going to be bigger than potassium, so that means that that potassium is going to form the stronger bond, so potassium goes. And then now when it comes time to thinking about magnesium and cesium, you can see that magnesium is a 2+, and cesium is a 1+, so that means that the 2+ will form the stronger bond, so that guy's out. And then now we're really considering between cesium fluoride and strontium oxide. Oxygen is bigger than fluorine and has a 2- charge, so there's kind of competing differences there. And then cesium is larger than strontium and has a smaller charge. So I think overall, because the product of the charges of the strontium oxide is so much bigger than what we see in cesium fluoride, then cesium fluoride is going to be the one with the weakest bond, because we have the biggest cation and the smallest charges. And it's pretty typical that you're going to decide this on the basis of the charges first and then the radii, because the charge varies a lot more than the radii does. So let's see what the answer from OpenStax was, and they said that it was D as well. So it's important to realize that ionic compounds form crystalline solids, where the ions are organized in such a way as to maximize attraction between the opposite charged ions and minimize repulsions between like charges. So if we look at this sodium chloride crystal here, you can see that the ions that have opposite charges are closer together than ions that have the same charge. And so here you can see two chlorides, and they're quite a way away from one another in comparison to the distance between the sodium and the chloride. So we're going to maximize attractions by keeping the oppositely charged ions close, and we're going to minimize repulsions by keeping those with the same charge further apart. So typical questions would be something like this one from OpenStax. It says, why is it incorrect to speak of a molecule of solid sodium chloride? And the answer is quite simple. There are no molecules in an ionic compound, because ionic compounds exist as crystals where we have an extended array of oppositely charged ions. So there are no molecules, they don't exist. There's no discrete little bundles of NaCl. There's just an extended crystalline lattice of sodium and chloride ions. So something like this, it says sodium chloride consists of discrete ions arranged in a crystal lattice, not covalently bound molecules. Okay, so another type of question that you might be asked is to predict on the basis of formula whether a compound is ionic or not. And so what we want to be mindful of is that an ionic compound is always going to involve a metal and a non-metal. And typically the formula will begin with that with the atomic symbol for a metal. The only other possibility is that you have a polyatomic cation, and then some kind of other anion. The most common polyatomic cation would be the ammonium ion. So we'd be looking for the formula beginning with a metal or beginning with NH4. So which of the following are ionic and which are covalent? So this one begins with chlorine, so that's a non-metal, so that's going to be covalent. This guy's beginning with manganese, so that's a metal, so it's going to be ionic. This is beginning with nitrogen, which is a non-metal, so that's going to be covalent. And this is beginning with cobalt, which is a metal, so that's going to be ionic. Okay, so there we go. All right, so that concludes section 7.1. I hope you found the video helpful.